So we're going to talk about the applications of logarithmic functions or logarithms, period. And I think a good place to start would be to say that logarithmic functions and exponential functions undo each other. And they're inverses of each other. Like we know, okay, maybe let's explain this. So we know if we have a function, like so let's say we have y equals b to the x power, and we want to find the inverse of this. What we do is we switch x and y, and then we solve for y. And there's a whole reason behind this. It's basically because the inputs of a function are the same as the outputs of its inverse function. So that's why we switch the inputs and the outputs, the x's and the y's. So doing that, right, this is the original. This is original. So I'm using a mouse to do this original, and then this is going to be the inverse. So we're going to switch x and y. So that means x is equal to b to the y. Now we know how to solve for y here. We would use logarithms. We can use a logarithm loop trick, right? We can do it like this, and then we would say that log. I know how to write log base b of x equals y. So I'm just going to put y equals it, okay? And so what that means is that these two things here, these are inverses of each other. Now, let's look at what that looks like graphically and what the implications of that are. Okay, so here I have, and I'm just choosing the base of 2 here so we can see something that's fairly common. Is we have in purple, this is, or actually let's just put the black line in first. Here is the graph of 2 to the x. Okay, y equals 2 to the x. And b could be any base, in this case it's 2. And here is the graph of log base 2 of x. Now, y equals log base 2 of x. Now, a property of all inverse functions that are inverses of each other, is that they are reflections about the line y equals x on a coordinate plane. And also, like we mentioned this a minute ago, is that the inputs, so here I have this table, the inputs of this original function, so x, this original function is 2 to the x, right? 2 to the x. They are the same, so here's the inputs, they are the same as the outputs of my other function, the inverse function. The inverse function in this case being log base 2 of x, because b is 2. Okay, and so what it does, it allows us to kind of say the similar thing, but instead of going one way to calculate for the function, we can go the other way. And what it also lets us do is something pretty cool. We can sort of transform data that is exponential and represent it and apply like a logarithmic transformation to it, and so it can be represented in a little bit different way. And it's this property that has enabled or is so ideal for using logarithms to represent certain things in science, which we'll talk about. Here is kind of a visual representation of what that is. So here we have basically the same thing we had on the previous slide. Just a limitation to the code that I wrote for Decibels is that I can't see the rest of this domain of this exponential here. But if I apply a logarithmic transformation to the y-axis, I'm going to apply a logarithmic transformation to the data that represents this black curve here. It looks like this. So it takes this black curve and basically flattens it out. So anything that was exponential in an exponential function, if you apply a logarithmic transformation to it, it's going to show up as a line. Now, the y-axis here, these labels are now no longer correct. And the y-axis is effectively kind of faux become logarithmic. Let me show an example of why something like this is relevant. And actually, if there's a few examples, but here's one that's very current. So here's data from this is data from Johns Hopkins website about the number of cases of COVID-19 in the United States. This is just the United States, and you can see that at the start it was a very flat flat curve here. We actually had the first case was reported, so it doesn't really start taking off until like, I don't know what time. There's only 24 cases in March, and then suddenly, like right in here, we start to get really exponential in the growth of this curve. And so based on what we just saw, if we were to apply a logarithmic transformation to this, then we would be able to see that this section of the graph should become kind of like a straight line then. And then if that's the case, this section of the graph here that looks a lot more linear, this would probably go the opposite direction. So it actually would take on more of a logarithmic shape from a straight line to a logarithmic shape. So let's see if that's the case. If you apply this, oh yeah, look. So we've got, so like again, we were kind of looking at this was the area where it started to grow exponentially. And we have basically a straight line there. And then you see that curve really starts to flatten. And this is a good thing here. Now, notice the y-axis is logarithmic, a base 10 logarithmic. It starts at 1, then 10, then multiply by 10, multiply by 10, multiply by 10, multiply by 10. So it's not like this is great or anything, but it's a different way to represent the data that may be more useful. We're still talking about the applications of logarithms. And I mentioned that ability for us to take something that is exponential in nature and kind of transform it into a linear representation has been great for creating these scales in science. And three of the most prominent ones that we use logarithms for, that's certainly not the only ones, but three of the most prominent ones are the pH scale, the Richter scale, and the decibel scale. And so in the case of the pH scale, you can see that the difference, like the concentration of hydrogen ions in the in a solution is when we go from one pH level like 14 to the next, it's 10 times greater. Okay, so this is negative 14, this is negative 13. So that means we multiplied this by 10 to get to here. So there's a 10 times increase. And so if we compare something from like up at this side of the scale to this side of the scale, it's a massively, I don't even know what 10 to the 14th is. I don't know I don't know what the prefix for that is, but it's hugely more concentrated of hydrogen ions. And so that's a way where we can say, all right, instead of it being whatever times 10 to the 14th times less, we just say it's 0 to 14. And so we can use this linear scale from just 0 to 14 to represent this very exponential relationship. Richter scale, same thing. So the difference between a magnitude 6 earthquake and a magnitude 7 earthquake, for example, is that the magnitude 7 earthquake is 10 times as powerful. And something that's cool here, like it's hard to wrap your head around some of these numbers, but this Chilean earthquake in 1960, called the Great Chilean Earthquake, had a magnitude of something like 9.5. And to put that into perspective a little bit, like a magnitude 10 earthquake has approximately 50, the equivalent like destructive force is about 56 trillion kilograms of TNT. And so what does that mean? Like, Wile E. Coyote in the cartoons, he would have like sticks of dynamite, and a stick of dynamite is something like, I think it's like 190, I can't remember now, but it's like not even a kilogram of TNT. So it's like a stick of dynamite, say it's like 100 grams or something. And so we have, to put this into perspective a little bit, are the largest atomic bomb that we ever made was about 50 megatons of TNT's worth of destructive power. That was the Tsar Bomba, and that was set up by the Soviet Union in the Arctic Circle way back when. Now, okay, how does this number compare to this number? Well, there's 1,000 kilograms in a metric ton. So what this says is that if we had 50 megatons, 1 trillion kilograms is not a megaton, it's a gigaton. So 1 trillion kilograms is 20 times more powerful than 50 megatons. And then 56 trillion kilograms of TNT is 56 times 20, or 1,300 times more powerful than an atomic bomb. This is at the same time, I think, very impressive and very frightening. It's impressive because we as a civilization, as it was a human race, were able to create something so powerful. But it's also frightening because imagine that amount of, it's very hard for us to wrap our heads around that amount of destructive force. Imagine that bomb was put up, was actually used for nefarious purposes, and then multiply that impact by 1,300. That is absolutely insane to me. And there's numbers that are difficult for us to comprehend. By the way, the way the Richter scale measures is it has a seismograph, and then it measures the wavelength here. So if we know from trigonometry, like the amplitude here, there's some number of microns, and we can and it's calibrated so that it picks up, it's able to read that height, that wave height, and then assign a Richter number to it, which is pretty cool. Also, decibels they're very similar in this way. So the difference between 30 decibels and 40 decibels is not just like a 10 decibel difference, it's 10 times as powerful. So the difference between something that's 30 decibels and 60 decibels is that it's 100 times more intense. So intensity is how we kind of refer to noise levels. It's a perceived loudness of something. And so when you start to really think about that, if the range of like where you start to potentially have damage to your eardrums is in like the 80 decibel range, well, like holy crap. I mean, so this is 100, this would be 1,000, this would be a million, 10,000, 100,000, million, 10 million. So like a gunshot or a siren at 100 feet, according to this, is 10 million times above, 10 million times more intense than the threshold we already have for like possible hearing damage and stuff. And that's pretty crazy. So let's actually look at how the math works for some of these things. So the Richter number, R, of an earthquake measures its intensity, I, compared to that of a teeny tiny reference earthquake, I naught. I naught would basically be as small as something could possibly be in order for it to register on the Richter scale on a seismograph. And so how does this work? Well, I want to compute the Richter number of an earthquake that is 2 million times more intense than the reference intensity. So what that says is right, the intensity of this earthquake is 2 million times the reference intensity. So we would go, okay, 2 million, is that million? 2 million I naught divided by I naught is saying, all right, then what is the log of 2 million? And we could type that into calculator. 10 to what power gives me 2 million? Turns out it's about 6.3. 10 to the 6.3 power is 2 million. That is too many zeros there. I'm sorry. Oh no, it's not. It's the right number of zeros. Wow, I'm so good. So that's a magnitude 6.3 earthquake. Similar math here for decibels. If a cat's purr is 316 times louder than the threshold sound again is like the minimum of is like our limit, the lower limit to what we can hear of perceived loudness. And so we would say then, it's the same thing, 10 times the log, and this 10 is a little different because of how we had, the Richter scale goes up by 1 each time. A decibel is like each level of decibels goes up by 10. And so 10 times the log of, we have 316 I naught, right? It's 316 times louder than the threshold sound. So what is, if we have 10 times the log of 316, well, I mean, I don't know exactly what this is, but I know that the log of 100 is 2, and I know that the log of 3.16 is probably close to 0.5. So let's say it's about 10 times something about 2.5. You could totally just plug this into a calculator and you get the answer. It's going to be somewhere around 25 decibels. So a little kitty purring is about 25 decibels. And yes, I do have a picture of my cat on this slide. Oh my God, how precious is that kitty right there? She's so precious. She's a princess. Can I draw a crown on her head there? Yeah, there you go. Okay. Now here's another problem. This is something that we've been able to solve before, but in doing so we had to do graphs. We had to draw two graphs and find their intersection points. And so what this is saying, right? Here's the formula we're using. A is equal to P times the quantity 1 plus R divided by N to the NT power. Okay. And so if we want to know how long it will take $500 to double if invested at 12% compounded quarterly, that means that P is 500, A is 1,000, N is quarterly, so N would be 4. That means we're compounding 4 times, and we don't know T. Oh, rate is 12%, so it's 0.12, and we don't know T. Okay, So we don't know t. So when we plug this in, we end up with 1,000. 1,000 equals 500 times 1 plus r is 0.12, n is 4, divided to the power of 4t. Okay, we don't know t. And now if we divide both sides, we see that 2 divided both sides by 500, we see that 2 is equal to this stuff, 1 plus 0.12 over 4 to the 4t power. Now we have an exponent problem here, so we can apply logarithms. This is the knowledge we have to solve for t. So why don't we take the log of both sides? In fact, let's just take the ln of both sides because ln is less letters. So I'm going to take the ln of this side, the ln of this side. That's going to give us the ln of 2 is equal to the ln of 1 plus 0.12 divided by 4 to the 4t power. Product rule lets me bring that exponent down. Okay, we can bring the exponent down in front. And so what we end up with is that the ln of 2 is equal to 4t times the ln of 1 plus 0.12 over 4, right? And then if we wanted to actually solve what that, we wanted to know what that is, well, we could do it. So what we would get is that well, we just also have to solve for t. So t is equal to the ln of 2 divided by 4 times the ln of 1 plus 0.12 over 4. Now the calculator will give us an answer to this of 5.86 years. Okay, so 5.86 years, which because we're compounding quarterly, it won't get that final amount until after 6 years. So we would say it was 6 years here. Now, this isn't necessarily nicer math, but it is just directly solving the problem without having to go through the graphing process. Here's like a similar sort of problem that we could do. We've been able to do before by graphing, or no, actually we had to use rational exponents. And this is not to say that this method is going to be preferred to that method, but it's just another way of doing it. So this is a similar problem here. We've got we want to know p. Let's write what we know. Right, p is 3,200. A is 4,000, and t is 3. We're compounding monthly, so that means n is 12, and we don't know r. Okay, so our formula for this, a is equal to p times 1 plus r divided by n to the nt power. So we've got 4,000 equals 3,200 times 1 plus, don't know r, divided by 12 to the 12 times 3 power. Okay, so if we divide 4,000 by 3,200, that's 5/4 equals 1 plus r divided by 12 to the 36 power. And so at this point before, what we would have done was take the 36th root of both sides, or we would raise both sides to the 1/36 power, same thing, and we'd be able to solve for r that way. But what we could do instead here, and again, this is not necessarily preferable by any stretch of the imagination, is we could take like the ln of both sides. So we could do, let's see, yeah, if we took the ln of both sides, would that help us? Yeah, we could totally take the ln of both sides. So if we had the ln, we take the ln of both sides here, the ln. This is not going to be pretty, but we can still do it. So the ln of 5/4 is equal to, we're going to bring the power of 36 down, 36 times the ln of 1 plus r over 12. And then we can divide both sides by 36. So we'll have the ln of 5/4 divided by 36 is equal to the ln of 1 plus r to the 12th. Now what we can do is actually do the other thing where we can take the e of both sides here. So we can say we're going to like raise both of these to like the e power kind of, or say that these are both powers of e. So e to that power, e to that power. We're like taking the e of both sides here. So then what we have here would be e to the ln of 5/4 divided by 36, which is horrible, I understand, but it's still a calculatorable number, is equal to 1 plus r over 12. Because if we say log base e of 1, so like log, there's an e right here, right? Log base e of 1, like what power has to raise e to get to 1 plus r to the 12th? Well, it's end up going to be just 1 plus r to the 12th. So if I raise e to that power, I'll get 1 plus r to the 12th. So that's what we have here. If we just need to solve this for r, we would say it's 12 times e to the power of ln of 5/4 divided by 36 minus 1, right? Oh wait, too many parentheses. So that. Horrible, right? But that's what r is going to be. It turns out for this problem that r is going to be, I don't know what r is, let me check. R is going to be 7.46% if you plug that into the calculator. So just another way of solving that problem. I don't know that that's preferable to taking the 36 root of both sides, but this is another way we can use logarithms to solve.